Welcome to this scientific lecture on starch gelatinization and retrogradation. Today we're going to explore the fascinating physics, chemistry, thermodynamics, and material science behind why foods like sushi rice and bread change texture when heated and cooled. Before we dive into the transformations, let's understand what starch actually is at the molecular level. Starch is a polysaccharide, meaning it's a large molecule made up of many glucose sugar units linked together. Starch consists of two primary molecular components, amylose and amylopectin. These have very different structures and properties. Amylose is a linear molecule, essentially a long chain of glucose units. It typically makes up 20 to 30% of starch. Amylopectin is highly branched with many side chains, constituting 70 to 80% of starch. In nature, starch exists in organized structures called granules. Understanding these granules is crucial to understanding gelatinization. Starch granules are semi-crystalline structures ranging from 5 to 100 micrometers in diameter. They contain alternating crystalline and amorphous regions. The crystalline regions are tightly packed amylopectin chains held together by hydrogen bonds. At room temperature, these granules are insoluble in water and quite rigid. The hydrogen bonds between chains create a stable, ordered structure that resists water penetration. Now let's explore what happens when we add heat and water. This process is called gelatinization. Let me ask you a question. What happens to the granule structure when we heat starch and water? The answer is thermal energy. When we heat starch granules in excess water, thermal energy disrupts the hydrogen bonds holding the crystalline structure together. At temperatures between 60 and 70 degrees Celsius, water molecules begin to penetrate the amorphous regions. The granules start to swell as water breaks hydrogen bonds and gets absorbed. The gelatinization temperature for most starches ranges from 60 to 75 degrees Celsius. This is why cooking rice or making bread requires temperatures in this range. Water molecules are polar. They form new hydrogen bonds with the hydroxyl groups on glucose units, displacing the bonds between starch chains. This is a classic example of competitive hydrogen bonding. As water penetrates, granules can swell to 5 to 30 times their original volume. This dramatic expansion is what gives cooked rice and bread their characteristic texture. As heating continues above the gelatinization temperature, the transformation becomes more dramatic. With continued heating, amylose molecules begin to leach out of the granules into the surrounding water. This creates a viscous gel matrix around the swollen granules. The linear amylose molecules are more mobile than branched amylopectin. They escape from the disrupted granule structure and entangle with each other in solution, dramatically increasing viscosity. Scientists use a technique called polarized light microscopy to monitor gelatinization. Native starch granules show a characteristic cross pattern called birefringence. When this disappears, we know the crystalline structure is fully disrupted. Let's discuss the thermodynamics. Gelatinization is an endothermic process requiring energy input. Why is this? The enthalpy change is positive. Energy must be supplied to break the numerous hydrogen bonds in the crystalline regions. The entropy change is also positive. The ordered crystalline structure becomes a disordered gel with much greater molecular freedom. At high enough temperatures, the T delta S term dominates, making delta G negative. The process becomes thermodynamically favorable above the gelatinization temperature. Let's apply this to cooking sushi rice. What's happening at the molecular level? Raw rice grains contain rigid starch granules. When we add water in a 1 to 1.2 ratio and heat to 100 degrees Celsius for 15 to 20 minutes, the granules gelatinize. They absorb water, swell, and create the soft, sticky texture perfect for sushi. Different rice varieties have different amylose to amylopectin ratios. Short-grain sushi rice has lower amylose content, around 15 to 20%, making it stickier. Long-grain rice has higher amylose, 20 to 25%, and cooks up fluffier and less sticky. During gelatinization, starch can bind 2 to 3 times its weight in water. This water binding is what makes cooked rice moist and tender. The hydroxyl groups on glucose units form hydrogen bonds with water molecules. Now let's discuss what happens when we cool down the gelatinized starch. This reverse process is called retrogradation. Here's a question. Why does bread become stale or rice becomes hard when cooled? The answer is thermodynamics again. At lower temperatures, the entropic advantage of the disordered gel state decreases. The system can lower its free energy by returning to a more ordered, crystalline state. In freshly cooked food, amylose chains are randomly oriented and mobile in the gel. As temperature decreases, molecular motion slows down. After cooling, amylose chains begin to reassociate through hydrogen bonding. They align into parallel arrangements, forming new crystalline regions. This is retrogradation. Retrogradation is essentially a recrystallization process. The amylose molecules, which are linear and mobile, align themselves into ordered double helices stabilized by hydrogen bonds between adjacent chains. Amylose retrogrades much faster than amylopectin. This is because its linear structure allows easy alignment. Amylose retrogradation occurs within hours at refrigerator temperatures. Amylopectin retrogradation takes days or weeks because its branches hinder alignment. As chains reassociate, water molecules are squeezed out from between them. This is called syneresis. This explains why refrigerated rice or bread feels dry and firm. The water hasn't evaporated. It's been expelled from the starch network. Let's discuss the kinetics. Retrogradation rate depends on several factors. Retrogradation is fastest at 2 to 4 degrees Celsius, which is refrigerator temperature. This is why refrigerated bread and rice stale so quickly. At freezer temperatures below -18 degrees Celsius, retrogradation is very slow because molecular motion is severely restricted. Water content matters. Retrogradation is fastest at 30 to 60% moisture. Very dry or very wet starch retrogrades more slowly. This is why bread left at room temperature and low humidity can actually resist staling better than refrigerated bread. Higher starch concentrations accelerate retrogradation because chains are closer together and can more easily find each other to form crystalline regions. Let's examine bread staling as a case study in retrogradation. Fresh bread has a soft, elastic crumb structure with gelatinized starch holding water. After 24 to 48 hours at room temperature, starch retrogradation causes the crumb to become firm and lose moisture to the surface. Here's a crucial point. Many people think bread goes stale because it dries out. Actually, the total water content barely changes. Staling is primarily due to starch retrogradation, not water evaporation. The water is still there, just redistributed. This is why you can refresh stale bread by heating it. Heat disrupts the newly formed crystalline regions, regelatinizing the starch. The bread temporarily becomes soft again. But it will stale even faster the second time because the starch chains are already partially aligned. From a materials science viewpoint, we're dealing with a fascinating phase transformation. Gelatinized starch forms a viscoelastic material with both viscous and elastic properties. The elastic component comes from the swollen granule network. The viscous component comes from the amylose solution. Retrograded starch has a glass transition temperature around 50 to 70 degrees Celsius depending on moisture content. Below this temperature, the material is glassy and brittle. Above it, it becomes rubbery and flexible. This explains the texture difference between room temperature and refrigerated rice. We can characterize this with rheology. Fresh gelatinized starch has a storage modulus G' greater than loss modulus G double prime, indicating gel-like behavior. As retrogradation proceeds, G' increases substantially as the structure becomes more rigid. Let's return to sushi rice and see what happens after refrigeration. Fresh sushi rice is sticky and soft. After 12 hours of refrigeration at 4 degrees Celsius, rapid retrogradation occurs. The rice becomes hard, loses its stickiness, and develops a grainy texture. This is why sushi should never be refrigerated if you want optimal texture. Interestingly, even though sushi rice has low amylose content, that amylose still retrogrades quickly. The low amylose actually makes the texture change more noticeable because there's less of the sticky amylopectin gel to maintain the desired texture. Are there ways to slow down or prevent retrogradation? This is important for food industry applications. Adding fats or emulsifiers like monoglycerides can slow retrogradation. These molecules form complexes with amylose, essentially wrapping around the chains and preventing them from reassociating. This is why commercial bread contains emulsifiers. Sugars and polyols like glycerol lower water activity and disrupt hydrogen bonding. They compete with starch for water molecules, slowing the recrystallization process. Freezing at -18 degrees Celsius or below stops retrogradation almost completely because molecular motion is arrested. This is why frozen bread can be stored for months without staling. Chemical modification of starch through cross-linking or substitution can prevent retrogradation. Modified starches are used extensively in frozen foods. Scientists use differential scanning calorimetry, or DSC, to study these transitions quantitatively. The enthalpy of gelatinization typically ranges from 10 to 20 joules per gram of starch. This is the energy needed to disrupt a crystalline structure. The enthalpy of retrogradation is lower, 2 to 8 joules per gram, because the retrograded structure is less ordered than native starch. The crystallites formed during retrogradation are smaller and less perfect. DSC gives us precise gelatinization temperature ranges. For rice starch, onset is around 65 degrees, peak at 73 degrees, and completion at 80 degrees Celsius. At the molecular level, we can think about the dynamics of individual chains. During retrogradation, amylose chains associate to form single helices in the presence of certain ligands, or double helices in aqueous solution. The double helix has 6 glucose units per turn and is stabilized by inter-chain hydrogen bonds. Amylopectin retrogradation involves the side chains forming crystalline lamellae. The branch points prevent complete crystallization, which is why amylopectin retrogradation is slower and less extensive. Water acts as a plasticizer, increasing molecular mobility. This is why intermediate moisture levels promote fastest retrogradation. Too dry and chains can't move, too wet and they're too diluted to associate. Let's look at mochi, a Japanese rice cake, as another fascinating example. Mochi is made from pounded glutinous rice with very high amylopectin content. Fresh mochi is incredibly soft and stretchy, but after just 24 hours at room temperature, retrogradation makes it hard and brittle. This dramatic change demonstrates how powerful retrogradation can be. Mochi hardening is almost entirely due to retrogradation with minimal water loss because its high moisture content. To refresh hardened mochi, you must heat it to regelatinize the starch. Toasting or microwaving works perfectly. Let's bring everything together into a comprehensive summary. Native starch exists as semi-crystalline granules held together by extensive hydrogen bonding networks. Gelatinization occurs when heat and water disrupt the structure. Granules swell, absorb water, amylose leaches out, and a viscous gel forms. The process is endothermic, but entropy-driven at elevated temperatures. Retrogradation occurs upon cooling as amylose and eventually amylopectin chains reassociate into crystalline structures. Retrogradation kinetics are fastest at refrigerator temperatures with intermediate moisture content. The consequences are dramatic texture changes, water expulsion through syneresis, and increased firmness that we perceive as staleness. These principles extend beyond just food science. In pharmaceuticals, starch gelatinization and retrogradation are used to design controlled-release drug delivery systems. Retrograded starch forms films with improved mechanical properties, useful for biodegradable packaging materials. The textile industry uses starch as sizing agents, and understanding retrogradation helps optimize fabric finishing processes. Let me pose one final question. If you had to keep rice or bread fresh for a party tomorrow, what's the scientifically optimal storage method? The scientifically optimal answer is room temperature storage in an airtight container. This avoids the rapid retrogradation zone of refrigerator temperatures while preventing moisture loss from the surface. For longer storage beyond 2 days, freezing is better than refrigeration. Starch gelatinization and retrogradation represent a fascinating interplay of chemistry, physics, and thermodynamics. Understanding these processes at the molecular level allows us to control food texture and quality. From the hydrogen bonding networks in native granules, through the entropy-driven swelling during cooking, to the thermodynamically favorable recrystallization upon cooling, every step involves fundamental scientific principles. Next time you eat sushi or toast bread, remember the complex molecular choreography occurring at the microscopic scale.